Hello everyone, this is lecture 15 of PTRE 451545. Today we should finish module 2. We might even start module 3. If we do start module 3, it won't be the exam. Okay, so don't worry about that. Homework 3 is due on Friday midnight.
Tomorrow.
Yeah, tomorrow.
Day Friday, I thought Friday is still far.
I will talk to you about the homework, but also I need to make a Blackboard announcement about the pairings because Kalu didn't receive any emails yet about the project pairings, the pairings for the project.
What is last week? You said we should pair ourselves.
No, I said that on Tuesday.
Yeah.
I didn't say it
Tuesday.
last week.
Oh, yeah, last class.
Oh,
rather.
yeah.
I forgot.
Yeah,
Send an email to Kalu. I told him to make up a spreadsheet.
How many pairs do you?
You said two.
Maximum of two.
Two.
Yeah. If you want to do it on your own, I'm open, but it's better if you do it with two. And I guess you need to have access to the app between you two guys. One of them should have access to the app somehow. Okay, about the homework, I think I made it a little bit harder than what I wanted to. I didn't want to give it away completely, but I don't want to, at the same time, I don't want to cause any misunderstandings, because if you make the first question wrong, everything will go wrong after that. So I did try to say it last time, but when you do the flow test, the data that you get, when you linearize this equation, I want you to plot this for Q and this for delta PX, okay? These are delta P total, but you need to plot it as delta PX. Don't do 4,000 minus this, 2, 3. If you will know that you did it right, if you get an n of less than 2, but close to 2, something like that. That's how you know that you are correct at that point. It's a power law fluid, that's why. Yeah, because if you make those wrong, everything will go wrong after that. That's why I didn't want to give it away completely, but I also don't want you guys to make a mistake on the first one because everything will go wrong after that. Yeah, the rest should be okay.
What some of us did, so that because we are already solving it, so that there's no problem and I can really know. Me, I was thinking, since in question 2 you gave us the delta P bit.
Wait, yeah.
So me, I used these parameters to calculate my delta P bit. Then I now subtracted it from the total to get my delta PS. That's what I now plotted against Q.
That's correct for the wait.
Yes,
for question number 2, you calculate delta PB.
No, for number 1, I used the formula you gave here, number 2, to calculate my delta P bit.
But you don't have Q, you don't have A. Well,
the diameter was given in question 1.
Yeah, you have A,
Yeah.
but yeah.
You saw for A first.
You saw,
So I can get A.
So if you get the area first.
it might have worked this way, but I don't know the numbers that you got, if they are correct.
For my, I don't know if I can say it in class, my hand was around 1.6 something. I don't know
What
if
was
another person
Your
gets it.
N
My
was
end
what?
was around my end was around 1.6 something.
I think mine could say
Similar. I don't know if and my Q was around the 0.05.
No,
Let me check mine.
mine is a little bit different.
for the N.
Yeah, for both. Let me see the solution here I sent to Kalu.
Yeah, 1.6744. That's about it.
You got 1.6744.
Yeah.
Okay. What did you get?
I think you can run that.
You might have gotten the same, I think. I got.
Because me too, I was confused that because the delta P total is different from delta P. Yeah, I was just wondering.
Yeah, the issue is that the way the explanation I gave last time, I made it sound that this 4,000 number is delta P total, but it's not the case. It's how high the pump can go. And I made it sounded very wrong.
Yeah, from my plot here is I have my N to be 1.6744. Yeah.
So you guys agree? That means you
Okay.
did it with two different ways and you got the same answer, which is a good sign. Okay.
So does that mean what I do
can
now,
work.
I will get my full mark?
Well,
Well, I want to get.
I
want to
think
get
if you
your
did,
full mark.
if you did everything later, correct,
Mm.
with these numbers, I don't know what is K, I don't have K here on this file. Can you tell me the
K?
intercept, the slope? Sorry, you told me the slope, give me the other number, the intercept.
My answer is minus 2.9924.
You got
Minus 2.99.
2.924, so, I mean, oops, wrong. 9924, you said.
Yeah.
Okay, if you did everything correct after that, I think you are gonna.
Yeah, I think I might intercept.
Yeah, you guys did it different ways and you got the same answer. So that's a good sign. So it works. It should work. It's cyclical, you know. You use the same equation. I guess you got A, you got rho, you got C. Yeah, I forgot that I also gave you the nozzle diameter is 13. Yeah, so you have it. Yeah, so it should work this way. But it should work if you linearize and plot the way I showed you guys.
Mhm.
You ln both sides and you plot it.
Mhm.
You should get, I mean, you got the same answer with Kim. So that should be a nice cushion to have. So both ways work. That's the whole point. Okay, but what I said last time, I made it sound like 4,000 is the delta P total. This is not correct for sure. Huh? It was really wrong. I thought about it later. Anyway, that about homework 2. Any questions on the homework 2? Homework 3, sorry. Donald, all good on homework 3?
I haven't started it yet.
Huh?
I haven't started it yet.
Yeah, not yet started.
Oh, okay, yeah. Okay, should be quick. Okay, so let's move on to homework, to our module 2. Last time, and I'm sorry that the videos are going fast because they were pre-recorded, and when I was doing them alone 2 years ago, I was doing them fast. But I think it was Roxanne who asked, like in real life, do you like stop as many times as I stopped to check to make sure that there is no flow back? And the answer is you stop often when you want to make sure, but that time that the ROP went down, I wouldn't have stopped in real life, let's say. Also, in the simulator, you speed it up 15 times real life, and you don't see when the connection is made. So connection, generally when they are drilling, they stop, they make the connection, jerk the chain, etc., and they are proceeding like that. So we did see the video. If you want to watch it again, I have the link here. We stopped twice. We checked for flowback, and then it was okay. Then we got a kick, right? And you saw it as yellow at the bottom. Now, what will happen if you get a kick and you ignore it? Like, okay. You see, I have, look at the screen here. As I'm drilling, this formation, the kick formation is here. You are gonna get a kick after you pass that point. You pass this point, this is one formation. This is another formation, and you will see the ROP changing. Now I'm starting to drill with the same process I said earlier. Circulate, rotate, add weight on the bit. Look at the yellow line, it's the ROP line. Once I pass this stage, it's gonna change. It's gonna go down, I think. Yeah, it went down. But my flow in equals to flow out, so I'm good. Everything else looks okay. Now it's gonna go up. This is a soft formation that we're about to get in now. So ROP will go up by a bit. But my flow out is good, so I don't stop. And I will soon get a kick after I pass that marble looking like, so I slow the simulator down. Look at the yellow spots here. They are gonna get bigger and bigger and bigger because now look, I get 432 out, I only put 418, so I am in trouble. Also, my ROP increased. My ROP increased here at the bottom. I'm ignoring it. I'm young, I haven't noticed it. Somebody's saying jokes on the rig floor. And the kick gets bigger and bigger and bigger and bigger. Yeah, flow out is bigger than what I'm flowing in. Also, the active pit gain has gone up. It doesn't look like it, but it has gone up. The active pit volume. So look at the yellow, it's going up. It's increasing and also it's moving up. I'm ignoring it. I keep drilling. Look at the flow out, how huge it is. And now suddenly my column is getting lighter and lighter because this is really a gas kick. And I'm gonna get a blowout. Very soon. I can still save it if I notice it now, but it's like the Arabic coffee. If you leave it too much on the stove, it comes up. There you go. You see?
Okay.
Yeah, now it's coming up.
The fluid.
Yeah. Now it's going to become a blowout.
But the BOP can hold it now.
Now it's too much. It would be hard to. Yeah, it would be hard. There is so much. I mean, you cannot fill your whole annulus with gas. I mean, it might work, but it might give you trouble. You know. Now it's a blowout. Okay, so I didn't do my job right now.
I have a question.
Yes,
How
sir.
long between the onset of kick till a blowout occur?
Oh, that's a case. It's a very good question, but it's a case by case. There is no direct answer. It might be. It depends on the rock formation, what kind of fluid it has, the pressure. It depends on what's your weight, what's your mat weight. I mean, what is the depth. Also depends on the clearance that you have between the annulus. How big is the annulus? If it's a very big annulus, it needs a lot of gas to get taller and taller because it's the height that matters. The problem is that even if you shut in the well and you're dealing with a gas kick, you have a fluid that its density is lower than the mat. So it's gonna want to rise on its own. So you may have shut in the well and you think everything is okay, but the kick is migrating up. It's migrating and it's getting bigger and bigger as it goes up. It's basically bringing reservoir pressure up to the surface. And this is very dangerous. It creeps on you if it's gas. Now, you may also have encountered a situation where they were drilling with oil-based mud and it was a slow kick. So the kick was entering the mud. It was dissolving in the mud. And they were drilling with the wrong mud weight, but they didn't know it because the kick was entering the mud. It was dissolving in the mud. And you don't get any indication of the kick like that, okay? Until you have a lot of gas in the mud cannot dissolve any other gas coming in from the rock, and then you get a kick again, you look at it as a separate phase, you know? That was oil-based macro. It was diesel, actually. No, it was some sort of oil-based macro. It wasn't diesel. It wasn't battery. But yeah, it becomes bigger and bigger. Also, back to your question, well, it wasn't really your question, but it was if you can save it when the whole annulus is filled with the kick almost. And I said the answer is could be. One thing that plays a role is where your casing shoe is. If your casing shoe is low, very low, if you had just run casing and cemented it and you did a good cement job and everything was fine, I mean, your vulnerable point is the casing shoe depth, which is basically the reservoir. So you are okay. That's what happened with my condo. They might have done a bad cement job, but at least the casing shoe was that low, and they were able to at least avoid the underground blowout from taking place. Because if you get an underground blowout, then you're in trouble. Well, that's when you are really in trouble because fluid is not coming out from your well, it's coming from the sides, and you would be in, that would be bad. Now, look at this animation. As the kick is moving up, it gets also taller, okay, because it's losing pressure. Yeah, it expands, exactly. And if it expands, it gains height. It's light, so it doesn't take a lot of density. So it doesn't add a lot to the mud weight, right, to the bottom hole pressure. As it goes up and it expands, what happens to the bottom hole pressure? It gets smaller and smaller. So what happens to the surface casing pressure as the kick moves up, you think?
It also increases.
It will also increase because it makes up what you are missing for the BHP to be equals to FPP, okay? So it's gonna be increasing, and there is a point where that value, say the casing shoe is here, okay? This is your casing shoe. That value here is equal, it corresponds to the pressure here being equal to the fracture pressure. Okay, this is what you calculated in homework too. In real life, we call it the MASP. And we're going to learn about it in module 4. It's the maximum allowable annular surface pressure. That means when you are circulating a kick out of the well, because you got a kick, now you need to circulate it. You need to be looking that the surface SICP is not higher than the MAASP. Because at MAASP MASP, the pressure at the casing shoe is equal to the fracture pressure. Then you have a problem if you are exceeding that. At the same time, you should not have the pressure on either side go below a certain value, because if it goes below a certain value, you're going to get more kick coming in. What would be that value, do you think?
What is the question?
What would be the value on either side where below that you get a kick coming in?
Okay, coming in.
Yeah. Remember, I got a kick. I shut in the well, and I get a value of SIDPP and an SICP. Then
the value, I think, will be equal to the pressure of the fluid that we just, of the formation fluid that we.
at the bottom hole, yeah. This should be equal to this. How do I make sure that this is the case when I'm circulating?
Then
It's a little bit more complicated. We're gonna see about that, but it depends on what kind of fluid you have. It depends on what kind of fluid you have. But if you have only mud weight, only normal mud, it should be equal to the original sharing drill pipe pressure. Because that's what is making the difference between what you are missing if you just have mud. If your whole well is filled with mud, no kick, but it can change. We are gonna see that in module 4 in more detail. It's a more complicated question. Maybe I shouldn't have made that question right now. But since we are on to it, what I was gonna say about the forgot. I'm gonna get back to it, I guess. Something I was gonna say about the yeah, we're gonna see how those values are varying. Anyway, I guess by now you all know about the Santa Barbara 1969 incident. That was a classic case of they didn't put very deep casing shoe. It was only a short portion, and then it was they got into trouble. And I have here the link to a JPT article. If you want to read more about it, sorry, not JPT, the Way Ahead article, basically saying what happened, blah, blah, blah. It's basically they didn't case enough portion of the well, and then you are dealing with a very long open hole section. That open hole section is vulnerable, is exposed. You want it to be as short as possible. Yep, and that was module 2. What did we learn? We learned about applying the YouTube modeling dynamic scenarios. That's basically the frictional losses. Construction of a hydraulic loop. We learned about dynamic mud weights, EMW, ECD. We learned about drilling fluids rheology. We learned about bit hydraulics optimization. That's what homework 3 is about. And we talked about making connections and route trip. We didn't really get into that much detail. I get into more detail in the first class, but that's about module 2. Any questions on module 2? Anyway, somebody in the office hours asked me a question, and I realized it would have been an easier way to explain it like that, is that when you construct a hydraulic loop, if you go with the flow, you subtract the friction, right? You always add if you gain weight, if you gain depth, you add hydrostatic, you subtract friction. If you lose depth, you subtract hydrostatic, and you also subtract friction because you are going with the flow. Now you can construct the loop the other way around too, by adding friction if you go against the flow. It's still possible. You can go from left to right, right? It is possible. Some people found it easier for homework 2 to go the other way around. And it's not wrong. It's just like you guys did with the homework. You did it in different ways, but you got the same answer. Yeah. So I guess hydraulic loop was the most important thing of module 2. Module 3. Okay. There you go. Module 3 is titled Wellbore Mechanics and Directional Drilling. And the first part, you two are going to find very easy because you already took, yeah, And we're going to be talking about how do you calculate those fractional gradients. Because we have used fractional pressure or fractional gradient, I just gave it to you, right? I gave it to you as a number, but you see in geomechanics and in even advanced simulations, it's a lot of numbers. It can be 4 different numbers, and you have to choose the lowest one or something. It's not as easy as what you are reading. Also, something that I was going to say, what I forgot to say when I was talking about the YouTube model, is that when you are dealing in real life, things are they are not like what we see in class. Like, for instance, I said about a stabilized shut-in drill pipe pressure. But what if that's changing too? We don't expect it to change, but it could be changing in real life. It really means something. It means that the kick is moving faster than what it should be, even, or what that is moving quite fast, or expanding quite fast, so that it's pushing on both sides. Theoretically, it shouldn't. It should only change the SICP. But these things are possible in real life. I mean, in the real world, things are changing that you didn't expect to change, etc., etc. You need to factor those into your decisions. Similarly, we do a leak-off test, and we get a value for the fracture pressure, but we may use a different kind of math, and then we could get a different value. You know, we need to account for these discrepancies. Like, we need to put safety factors. There is heterogeneity in the rock. Things are changing, and it's not easy. It's not like textbook-like case, you know. I mean, you need to be open-minded to these things. Like, similarly, there is several models to model fractional pressure. We are going to see 4 models in this module, if I'm not mistaken, 4 or 5. But there is much more than that. Much more than that. Yeah, we're going to see only the classics, but there may be Donald is undergrad. Roxon is didn't take geomechanics.
No, I didn't take.
Okay, some of the things you might see are a little bit new, but it's not crazy. The undergrads are gonna see those in more detail in the next class, so I don't get into those geomechanics part very in depth, but you know, it's an important subtopic. So when we are in the Earth subsurface, we are dealing with a stress environment. Okay, it's like you are dealing with a lot of compression, just like when you are in statics and solid mechanics. You are using tension as positive and compression as negative. In geomechanics, in rock mechanics, because you are in the subsurface, you have much more compressive stresses than tensile stresses. So you are going to use compression positive, tension negative. So it's different than your statics or solid mechanics class. So in the subsurface, the stress can be characterized in general by 3 compressive in situ stresses that are mutually orthogonal. And Anderson in 1904, he simplified everything into 3 stresses. And he said 2 rules. You have one stress that is vertical, and then 2 horizontal, and you call the horizontal, the stronger of the 2 horizontal, S uppercase H max, And the other one, you call it S, smaller case, smaller h, lowercase h, mean, okay? So the only law is that one is vertical and two horizontal, and the other one is that you call the strongest horizontal SH max, and the weaker horizontal in terms of compression SH mean. Well, 1951 was the book of Anderson, but the theory was from 1904.
Long time.
Yeah, it was a long time ago. But mathematically, if you don't use Anderson's theory, it can be very, very complicated. That's when we have S1, S2, S3. You need to do some processing mathematically that is beyond the scope of this class, like some ridiculous matrices. You need to know matrix algebra. I'm simplifying this into that. So SV is also known as the oververtex. It's the weight of the earth above you. Okay, how much the rock above you weighs, or the rock and the seawater above you weighs. The horizontal stresses are known as the tectonic stresses, and yeah, tectonic, or the horizontal confinement stresses, or just the confinement stresses. Okay, there is 3 fracture modes. If you took a class on fracture mechanics, you will have learned about those. These are the mode 1. That's the tensile, the open mode. Imagine taking chopsticks and then flipping them around and pulling them apart. That's the tearing mode, okay, open mode. This is the kind of fractures that we are dealing with when we are doing hydraulic fracturing, when we are doing leak-off testing, when we are drilling, the drilling-induced tensile fractures that we learn in geomechanics and advanced simulation techniques, etc., etc. That's mode 1. Mode 2 is the sliding in-plane shear mode. That is, you're pushing across. This is the kind of failures that you find on the faults when you have earthquakes. Also, when you have very long fractures, you have on the sides, on the walls of the fracture, a lot of mode 2. Hydraulic fractures are mode 1, but they are mode 1 at the tip. On the walls, they are mode 2. That's why you use microseismic. Microseismic doesn't see mode 1, it sees mode 2. That's why, but we can do microseismic when we do hydraulic fracturing, right? Even if it's mode 1. We call the mode 1 aseismic, I think. Now, mode 3 is the tearing mode. Imagine twisting, turning around and twisting the chopstick. And this is what the tearing mode is. It's out of plane shear, out of plane shear. Tearing mode or twisting mode. This is the kind of fractures that you see on the edges of a strike slip fault. I'm gonna talk about those in later. You know, like the San Andreas in California, you find a lot of mode 3 instances there. Now, in real life, like I said earlier, nothing is perfect. So you get, you try to do hydraulic fracturing, and it's not just mode 1, you get mode 2, right? You get mode 2 to the extent that you can use microseismic to observe it. So even when we do experiments and we are trying to create like an SCB test or a UCS test, and we try to model it in a software, we find all 3 kinds of failure when we are doing it. And this is expected because things are changing when you have failure. Now, some of you know more about the regimes, etc., normal faulting, strike slip faulting, reverse faulting. It really depends on where you are drilling. Now, how do you estimate the magnitude of SV? That's basically what I said earlier. You need to estimate the mass of the rock above you. And you may have some indication of the density of the layers above you and their depth or their thickness. And basically, you are solving this integral. And there is a not very well-paying subdiscipline of geology of structural geology called overburden estimations. And this is what they are doing. They are solving that integral. Now, this integral is basically, I take the density of layer 1, I multiply by the thickness, and then I add to it the density of layer 2 multiplied by the thickness, and so on and so forth. Overburden estimations, our chair has done overburden estimations for NASA in different planets back in the late 80s. When he was a postdoc there, they were interested about the geologic formations in Venus and Mars. But basically, you are going to ask a structural geologist. Every company has, every operator has somebody that is doing that or looks at data for that. If you have a density log, it's very easy to do. Or even an elastic properties log can give you enough information to do that. On average, it's not a law, but on average, the density, they messed up your screen. On average, the overburden stress gradient, we call it the lithostatic stress gradient, comes from the ancient Greek word for rock, lithos. That's the ancient Greek word. The modern Greek word for rock is petra. But anyways, on average, 1 psi per foot, it translates to 23 MPa per kilometer. What is the density equivalent in ppg for that?
Of 23 pp. It's not 8
ppg?
8.33.
No, that's fresh water.
That's fresh water.
We found that value.
It's 0.433.
No, that's psi per
That's-
foot
yes,
for fresh water. Remember, I calculated the value and I was like, that value is important because it translates to 1 psi per foot.
19.
Yeah, 19.23.
Yeah.
Okay, that's the value. So sometimes there was an old Petrobol question. I remember when I was studying that it was asking, what is the highest mud weight you can use? It was a very bad question. The answer was 19.23 ppg. But the reason is whoever wrote it thought that, okay, above that, you are over the 1 psi per foot. And you are lifting the overpressure. You are basically lifting the rock after that. But it could be bigger than 1. It could be 1.4. Right? There are places where doesn't mean that, I mean, okay, hypothetically you lift the overburden, but anyway. Good intentions, bad outcomes, you know. Anyway, you want to solve this integral, and you don't know how to solve it. Like you cannot solve it exact. You don't have enough information, so you need to basically approximate it. The summation on the right side is something that you are gonna use. Now, I advise caution. Well, everybody here is foreign, and I'm foreign too. And it depends. If you're using SI units that we use in Europe, you are gonna use something like MPa. You're gonna use kilograms per meter cubed for the density. Then you are gonna use meters for the Z values. And then you need to convert the kilograms to newtons. So you need to multiply by the G. And the G is like 9.81 newtons per kilometer, per kilogram, something like that. Okay, In that case, you need to use G. If you are using American units or oil field units, then your density is pounds per, I don't know, cubic feet. Then your Z is feet. Then it's like the density is pound mass per cubic feet, okay? How many pound force in a pound mass? How do you go from pound mass to pound force? Rock, how do you go from pound mass to pound force?
From mass to force.
Pound mass unit to pound force.
What is equal to mass times acceleration?
Yes, but in
Right.
American units, you don't need to do that. You don't need to multiply by G.
Why?
Because 1 pound mass in standard conditions exerts 1 pound force. Okay? Now, if you go online and you check what is G in American units, it's gonna give you something like 32.2 feet per second.
Second square.
Okay. And you will think that, okay, I do the same thing, but I put G 32.2. I will give you the wrong answer. If you use American units, you should not use anything for G, because you take the density in pound mass per cubic feet, you multiply by feet, then you are now with pound mass per feet square. Okay, you make the feet square inches square, then you have pound mass per inch square. Now make the pound mass to pound force. You don't need to do anything for that, just it's the same number. Okay? Then pound force divided by inch square is pounds per square inch. What is that? It's PSI. So you are already there. Now, if you multiply by 32.2, you are going to mess up your answer. That's why the first time I was teaching this class, no, the first time I was teaching geomechanics, there was a homework that they had to use this approximation, and it was a bloodbath, because some people thought, oh yeah, they go online, they see what is G in American units, 32.2, plug it in, it messed up the answer. It messed up the answer. Now, we said 1 psi per foot, 23 MPa per kilometer. For reference, fresh water is 0.43. And that is 9.8 MPa per kilometer, less than half. What is that in ppg? For fresh water. You said that earlier, 8.33 ppg. Okay, that's where the 0.052 conversion factor comes from. But this one is for rock, this one is for fresh water. Just telling you. Okay. So you are going to ask a structural geologist for information on SV. That's how you are going to get SV. Now we have two left. We have SH max and SH min. Oh, before that, what do we do offshore? We need to add the weight of the seawater above you. And this is another version of that approximation, because sometimes you have the value, the density of the layer, not from depth 1 to depth 2, but the density at that depth, because this is what the density log is giving you, the density at a given depth. Then you can use this equation then. So instead of, what am I saying is that instead of, it's the same approximation, it's just, okay. Layer 1, depth Z1. Layer 2, depth Z2. Layer 3, depth Z3. Not from 2 to 3, you know, not from this to this. I'm giving you the density at a specific depth. Layer N, density N, Zn. Okay, in that case, it's a different version of the same problem. You're gonna use this equation. Okay, it's just it's the same approximation, just the depth, the density not from depth above and depth below, the density at specific depth, depends on how the data that you have is. This is actually more likely if you are in the oil field that you will have to use this than the other equation. Gulf of Mexico, look, I made a typo. It says Gulf of Mexico. If you are in seawater, be careful. Take the weight of the seawater, add it to the first layer. Don't add it to every layer. That's another common mistake. If you add it to every layer, you take the weight of the seawater. You just need to add it to layer 1, right?
Yeah, sure.
And then you add layer 2, you add layer 3, you add layer 4, 5, and don't take the seawater and add it to every layer. It's going to give you a massive value for SV. Okay, that's a common mistake. Please don't do that. Okay, that's when you are offshore. That's why I made this slide. Calculating SV. You can plot SV on a stress traverse, on a traverse plot, just like we did with the pressure gradients, the mud windows, pretty much. Okay, now, okay, I think I need to draw something here. How do you think it's gonna look like if I'm onshore? Where am I gonna start from?
You're onshore.
Onshore, yeah, here. If I'm drilling here, what is my SV on the surface? It's easy.
Zero.
Huh?
Zero.
0. Very nice. And then how is it gonna look like, do you think? If it's constant slope, yeah. Straight line, okay. Now in, say I'm dealing with a 1 PSI per foot. We call those areas when SV is bigger than SH max and SH mean, what we call normal faulting in geomechanics, or even strike slip. Strike slip is in between. But if the SV is bigger than the SH max and the SH mean, we call these areas tectonically relaxed. That's how the Gulf is. Okay, tectonically relaxed. There is a reason why it's tectonically relaxed, is the way the sediments are deposited in a delta creates normal faulting. Okay, if this is 1 PSI, what should be the slope here?
That's 1 PS. The slope there should still be 1 foot per PSI.
Excellent, excellent, 1 foot per PSI. Now I want to draw a tectonically active area, like a reverse faulting or a strike slip. The Himalayas, you have mountains, right? Big mountains. This is tectonically active area. Okay, the horizontal stresses are huge compared to the overburden stresses. Santa Barbara was a tectonically active area. It was a strike slip faulting. So you have a lot of faults there, but it's not as tectonically active as Himalayas, let's say, or surprisingly, the east coast of the US is pretty tectonically active. The east coast of the US is reverse faulting. The west coast of the US, that's California and stuff, is also tectonically active, but not as much. It's strike slip faulting. That's the San Andreas and those stuff in California. The Gulf.
Is it because of those areas we have a lot, like a kind of mountains?
Well, you don't have, well, you have mountains in California, but it's more on that side, the east side. Well, you have mountains in the Himalayas, and that's a reverse faulting. Australia is a pretty tectonically active area. The Gulf is tectonically relaxed. Okay, the Gulf is tectonically relaxed. We are between here. We are between normal faulting and strike slip faulting. So we are in between. We are in between, very close. Yeah, I mean, so now, how about I draw a tectonically active, more tectonically active, a 0.8 psi per foot? How will this look like? Line. Where is it gonna start from if I'm onshore?
Not sure.
Yeah.
This stuff on 0.
Okay, excellent. Should it be like this or like this?
It should be a steeper slope.
Steeper slope. So how it should look like?
So come this way. This side, on the,
Like this
yeah,
or like this?
no, the first one.
The first one.
Yeah,
Okay.
of course, like,
What would be the slope?
1 divided by 0.8.
Yeah. And what units?
Feet per
PSI. It's like the hydraulic loop, remember?
1.25.
This is 5/4, I think, right?
1.25.
Yeah, it must be 5/4 or like, yeah,
I don't understand that.
yeah, 5/4.
Oh, yes, okay, that's what
Yeah,
I meant,
yeah,
yes.
P per PSI. Okay. Now, this represents a smaller gradient, right? A smaller lithostatic gradient. Remember, there was a little bit of a confusion when we were doing a hydraulic loop. After you go into the drill collars, the pipe becomes smaller, there is bigger friction, and the line becomes steeper because you lose more to friction. You have a smaller overall gradient, so it should appear steeper because this is feet over PSI, right? That's why. So if your PSI over foot becomes smaller, the line should become steeper. That's why when you see something like that, when you see a line going from orange to purple, it really indicates under pressure, right? Under pressure, the pressure goes down at a given depth. Okay, that's a little bit counterintuitive. That's why I wanted to show it. The overburden, though, is not always the least compressive stress. Now, it's going to be cleared up later, but when you are doing a hydraulic fracture or a tensile fracture, or when you are doing a leak-off test, the fracture you are trying to induce is a mode 1 fracture. Okay, those fractures, they open against the smallest of the 3 stresses, like SH mean or SV. It cannot be against SH max because SH max is always bigger than SH mean. So you need to figure out which of the 3 stresses is the least compressive, either SH mean or SV, and this is how the fracture is going to open. Now, many times SV is not the least compressive, just like in normal faulting, just like in strike slip faulting. So you need to see how the fracture will initiate. And this is a very popular YouTube video that shows an experiment in gelatin. You guys have seen it before. Rock has not. No. Okay, these people, I think it's a girl, she's trying to make an experiment in gelatin. So this is a low concentration gelatin. The experiments that Kalu is doing is much denser gelatin. But gelatin has this ability that if you mix it at high concentrations, it starts becoming resembling the properties of a rock. It scales well to do experiments there on rock. It behaves like a rock. And then if you do it at a very high concentration, it becomes a even ballistics gel. You know, you can shoot and it can catch the bullet. It becomes very it's very similar to a human, the human body in a sense. But anyway, the good thing with gelatin is that because it resembles like rock, rocks are very brittle and they can crack in a tensile manner very easily or fairly easily. The gelatin can do it even easier, so you can use it in the lab. Now, what this lady is gonna do, she has this, it resembles a reservoir, a jar full of solidified gelatin. She's gonna go in with a straw and try to inject a juice or something. She's gonna do it at a shallow depth where the overburden is not higher than the confining horizontal stresses, and the fracture that she's gonna get is flat, pancake-like fracture. This is because the way the fracture would open by doing work against the smallness of the stresses. In that case, it's the overburden. So it's opening up, the thickness of the fracture would be parallel to the overburden stress. So it's a pancake-like fracture. Then she's gonna take the straw out and go deeper, go back in it again, deeper, much deeper, where the overburden would be higher than the confining stresses, and try to make a fracture lower, and then the fracture is gonna look different. It's gonna look like more like axial to the web. The width is gonna be on the width would be perpendicular to the web. Yeah, you will see. You will understand when I see. We don't care about the music. She goes not very deep, and look at the fracture. Look at how the fracture is. Okay, how did it open? It opened in the direction of the overburden stress because overburden was the smallest. How do I write? So let's just call this fracture is like this, right? Okay, it opens like this. It's the width of the fracture that matters if you are a mode 1 fracture. The width is in the direction of SV, right? SV, say SH max, SH mean. Okay, the smallest is this. So the arrows, the width of the fracture is in the direction of SV, right? You see that?
Mhm.
Okay, very important. Now, when you go deep per, oh, I pressed the wrong. Now she's gonna go again deeper. Look at that. She's gonna go deeper and inject. Look at the fracture now. Very different, right? And now she's gonna rotate the jar. Look at the width of the fracture. The fracture, she's showing you the width of the fracture, is basically opening like this. You are opening against a horizontal stress because SV, SH max, SH mean. Now you know that the least is SH mean, is no longer SV. So she's opening against SH mean. Well, actually, if I'm right, I'm gonna do it as, let's call this SH mean and this SH max. So you see this is in the same direction as these stresses, right? How you are opening. You are opening, so it's the width of the fracture that matters. The thickness, not the width of the fracture, the thickness, how it opens, the smallest dimension. So if If, let me see, oh, excellent. I will get a page here. Okay, if this is the fraction, all it matters is this. The direction that this is on, so say in this case is this direction. This is my direction of the smallness of the stresses. Okay. Now, if the smallness of the stresses was vertical, the fraction is like this, right? But when she went deeper, it was like this. The smallness of the stress was vertical. Excellent. Very nice video. And I have an explanation in the comments explaining what happens here. In the 80s, in California, sorry, what are we seeing here? They were drilling a lot of wells in diatomite. You know, diatomite is basically kitty litter. And they were trying to fracture them. It was vertical well. They were trying to get something like this. Okay, this is what they wanted. It was a frag and pack job. But diatomite is very light, and very often we're getting this. Sorry, this transverse fracture, as we call it. And I know somebody from LSU, he got a patent by saying, by finding a way to where you are getting a fracture like that, instead to use a small one to increase the overburden, and then go below it and get a longitudinal one. And that pattern is from '89, and it's still working even today. Anyway, that about fractures. We get deeper on fractures in other classes, so I don't go very, very deep into it in this one. But yeah, so know about the slopes and everything. You don't need to worry about these slides for the exam, but you're gonna have a nice homework 4 about that. Homework 4 is on fracture gradient. Homework 5 is on kick circulation. And then you have the 2 exercises for the project, and then the final, and the midterm that is coming up. Anyway, pore pressure is the pressure of the fluid inside your rock that you are drilling. And by now you know that this is an important value because you need to get your gradient, your mud weight to match that. For reference, hydrostatic pressure gradient is the gradient of the fresh water, 0.433 psi per foot, 9.8 megapascals per kilometer. Now for salt water, the Gulf is 0.65, but you can find others. I mean, in the Dead Sea is much higher, right? What is the density of the seawater at Dead Sea? It's much higher. Hey Siri, what is the density of the seawater at Dead Sea?
The density of seawater in the Dead Sea is 1.24 kilograms dm3. This is unusually high due to the salt concentration of the Dead Sea fluctuating.
So it's 24% bigger than the density of the fresh water. Hey Siri, what is 0.433 times 1.24? 0.54. 0.54.
Yeah.
So it's much, much higher. That's why you can basically see it on the water.
Without sinking.
Yeah.
Wow.
Yeah, it's very, very, it's very dense.
You can do it without not sinking.
Huh?
Sit on the.
Have you tried it?
No, I've never been to the Red Sea, to the Dead Sea.
Obviously,
No, you
I-
said it. You take it, run inside, you there.
So normal pore pressure is when your formation pore pressure is 0.433. Okay, we call that hydropressure or normal pore pressure. Now, don't confuse that with the hydrostatic wave. Okay, if I have a reservoir of a certain pressure density, right? And I say, what is the hydrostatic equivalent of that density? You are gonna take the pressure of the reservoir, convert it to density, and give me the value, right? You are not gonna take the density of fresh water and give me that value. It's a confusion because hydro comes from the ancient Greek word hydro, which means water. And that's ancient word. The modern Greek word for water is nero. But in the scientific community, when you say hydraulic or something, it's something that has to do with fluid. We use it for fluid. Like hydraulic modeling means fluid flow modeling. Okay, something about fluid flow. Doesn't mean fresh water. Okay, so if I ask you the hydrostatic pressure of this, it doesn't mean assume that this is fresh water necessarily. But if I can tell you, if I tell you the hydrostatic pressure gradient is this, it's 0.433, means that fresh water. It's used interchangeably, it's very confusing. So when you are answering a question in an exam and you see the word hydrostatic or something, you need to understand the context of what is it asking, because it can cause confusion. If I give you a reservoir to work on and it's 1,000 feet deep, don't assume that it's like 0.433 times 1,000. And then you come and you tell me that the reservoir pressure is 433. It's not the case. I mean, the hydrostatic pressure gradient is not necessarily that. Now, if I say it's normal, assume that it's normal pressure, you can assume that it's hydro pressure. I know it's very confusing. And sometimes I fall into these traps, but yeah, make sure. Now, if it's abnormal pressure, it means, or geopressure, it's a higher than the weight of the fresh water. It cannot exceed the overburden pressure gradient. That's where the 19.23 ppg came from. But it's, yeah, that's the difference. Okay. Now, when we are petroleum engineers, we are really going for these abnormal pressure reservoirs, right? This is what we are going after. Just telling you so that we don't have any confusions. I spent time in the other class explaining that the difference between. So remember when we were doing about the YouTube model, we are saying about you go deeper, you add more hydrostatic pressure. Okay. It doesn't mean that you assume that that weight is fresh water, right? But we still call it hydrostatic pressure, right? But we can say, oh, this reservoir is normal hydro pressure, or we mean 4.33. It's two different, and it's not, it's a mistake that they are using them interchangeably, but it's unfortunate. Anyway, now, again, I have a pressure traverse diagram. Sorry. How does the overpressure look like? The extra pressure. Is it an increase in the slope or a decrease in the slope? These are straight lines like the ones I drew last time when we were doing the first one. I drew an orange one and a pink one, remember?
Yeah.
And then I ask you guys, okay, which line, X or Y, has the biggest, represents the biggest pressure?
That's going to be the Y.
Correct? Very nice, very nice. Why the Y?
Biggest slope,
Smaller.
smaller, yes. Yes.
Remember the slope is feet per PSI.
Mhm.
Okay, so yes, it's the Y is a smaller slope. So look at this region B here. I go from one slope. Where is my pen? Look at the region Y. I go from this slope, let's say it's the same thing, and then I go to something much smaller, right? Smaller, my slope decreased. That means I went from low pressure to higher pressure. Now, what if my slope went like this now? What would that mean? Hypothetically speaking,
It becomes higher. The pressure becomes higher.
the pressure becomes higher.
From high to low.
Yeah, you go from high to low, the pressure becomes lower. High gradient, low pressure gradient. The other way, it goes the other way. Because remember, traverse plot, when you hear the word traverse, think the other way around. It goes like lower pressure. So I went from A to B, low to high. And then it went back to A in your diagram. It went back to normal. Okay, so this region here is the overpressure region. Now, how does it look like for pore pressure? We're looking at the red line. You see the increase? The blue line is hypothetical. It's the hydrostatic. Straight line, right? 0.433. That's the 0.433 PSI per foot I was talking about. Now, once you start separating, that's where you have overpressure. If you are working for an oil and gas company, this is what you are looking for, right? The accumulation. This is what you are going after. Okay, let's see other stuff. This one has, this diagram at the bottom has three things that I'm interested in while drilling. I have the lithostatic gradient, which is SV. I should not exceed it, otherwise I'm lifting the earth. I have the blue fracture gradient that my mat should not exceed, otherwise I have low circulations. And I also have the pore pressure. Sorry, cannot write at the red line is the pore pressure. This one, oh, I guess. Anyway, the red line, what does it show? The pore pressure. My mat weight should stay between the red and the blue, right? Remember, this is how we did casing design, right? In the past, in the first module. I stay between this and this, my mat weight. If I go here, what do I get? Huh? What do I get if I'm here?
You get a kick.
Yeah.
Below the
And if I'm on the blue side, on the other side,
Fracture.
low circulation, which eventually will lead to a kick. I will lose my mat, and then I won't have enough mud in the well, and I will get a fracture, a kick. Created by disequilibrium compaction. This is what you get when you have delta deposits. Some of you are taking petroleum geology. I think Donald is taking petroleum geology, right, Donald?
Yes.
Okay, you probably did about disequilibrium compaction. That's what you have in the Gulf when the sediment is basically, I forgot what they call that boundary in geology. But you have these sediment deposits, and pore pressure is trying to escape them. But you are depositing sediment, layers of sediment, faster and faster than what the pore pressure can escape. That's why Gulf of Mexico has a Gulf of America has a lot of high pressure reservoirs, right?
Yeah.
It has a lot of high pressure reservoirs because you have the delta in Louisiana is depositing sediment on top of sediment year after year, millions of years, and then the fluids are not able to. Are they waiting?
Yes.
Yeah, they are trying to escape the rock, but they are depositing faster than what they can escape. That's why you have normal faulting, and that's why you have high pressure reservoirs. This is other stuff that you are gonna learn later on in your other classes. Reservoir compartmentalization. That's when you have a lot of heterogeneity, and the reservoir is divided into different pieces. It actually causes overpressure. You can have high pressure there, but not high pressure here.
That is a heterogeneous.
Very heterogeneous. Very, very heterogeneous. Very real life. Aquathermal pressurization, radioactive decay of the matter, thermal kerogen maturation. You guys are doing those in petroleum geology, I guess, but that's things that are causing high overpressure, bigger than the normal pressure, which is the hydrostatic, the 0.433. Anyway, we're going to talk about fractal gradients after the exam. So when we come back, we are going to use the first lecture for review, and then we are going to have the exam. So please send to Kalu the pairings for the DS3. If you want to do it on your own, still tell him so that he notes you down. Yeah, and I might post the first part of the homework, which is the first part of the exam of the project that is in on the simulator before the exam, but I might not. I don't know. We're gonna see. Yeah, but study hard for the exam during the spring break. So when you come back, bring questions with you so that we can solve them
Together.
because this class only has one exam. I want you guys to do well on that exam.
Yes, sir.
And with that, thank you very much. And I will have a nice spring break. Don't get too drunk.
We drink, but we will not.
Yeah.
We will not drown.
I will see you guys on Tuesday. Oh yeah, I will see you guys tomorrow as
Yeah,
well.
tomorrow.
Yeah, tomorrow has a lot.
Yeah.
of
Oh yeah, tomorrow there is the lunch and learn with SP. Make sure you guys attend. It can be possible to attend with Zoom as
Yeah,
well.
yeah.
Yeah.
Online, yes.
Yeah. Thank you, everyone. See you.